Welcome to today's Explainer. We're jumping right into the invisible physics that hold our liquid world together. We see it every day, right? A drop of water clinging to a leaf, or bugs skating across a pond. But how do those microscopic forces actually work? And how on earth do scientists measure them in a lab? Let's dive in and unlock the science of surface tension.
So before we start looking at heavy lab equipment, we've got to ask a pretty fundamental question. How do we measure something we can't even see? We're dealing with intermolecular bonds that are vanishingly small, yet they dictate the physical boundaries of literally every fluid on Earth. To pull this off, scientists use some seriously clever experimental methods to translate those microscopic interactions into actual macroscopic data we can record.
Here's our roadmap for today. 1. The elastic liquid sheet. 2. The Noüy ring method. 3. Spinning drops in space. 4. The bubble pressure technique. And 5. Comparing liquid surface tensions. Let's get to it.
Part 1. The elastic liquid sheet.
Okay, so the crucial point here is that surface tension basically creates this tight, elastic-like membrane on the outside of a liquid. When a fluid meets another phase, like the air in this room, its surface resists breaking. It's all because of cohesive forces. The attractive forces between the liquid's own molecules pulling on each other. But why does it act like a sheet?
This diagram hits the nail on the head. Look at the molecules deep down in the bulk of the liquid. They've got neighbors on all sides, meaning they're being pulled equally in every single direction. Net force? Exactly 0. But look up at the top, right at that interface with the air. These surface molecules only have neighbors beside and below them. Because they're missing that upward pull, they feel a net inward force, so they associate much more strongly with the molecules right next to them. It's that inward tug that weaves the invisible elastic sheet we know as surface tension.
Moving on to Part 2. The Noüy ring method.
Check out the contrast here. On one side, we have this bulky, heavy-duty crust tensiometer, but the actual measuring component is just a delicate, super precise metal ring. In the Noüy ring method, we lower this ring into the liquid and then slowly, carefully pull it back up. Because of those cohesive forces we just talked about, the liquid surface stretches and clings to the ring, fighting that upward pull. The tensiometer just measures the exact amount of force it takes to finally snap that elastic barrier. It's a classic, highly effective mechanical test.
All right, Part 3. Spinning drops in space.
Now, instead of pulling a ring out of a beaker, the spinning drop tensiometer takes a totally different approach. It analyzes the interface between two entirely different liquids. To do this, you put a drop of a lighter liquid inside a heavier liquid, all inside a capillary tube. Then you spin that tube incredibly fast. This lets scientists optically measure the tension just by looking at the shape of the drop while it's spinning.
It's basically a microscopic tug-of-war. On one side, you have intense centrifugal force from that rapid spin pulling the drop outward, trying to stretch it out. On the flip side, the liquid's internal interfacial tension is fighting right back, trying desperately to keep that drop perfectly round. By measuring the drop's curvature during this high-speed spin, using mathematical models like the Young-Laplace or Vonnegut equations, scientists can calculate the exact tension holding the whole thing together.
That brings us to Part 4, the bubble pressure technique.
This one is the maximum bubble pressure method. Here, gas is pumped into a submerged capillary tube at a highly controlled rate. As the bubble grows, its radius actually shrinks, which causes the internal pressure to spike. That pressure hits its absolute peak right at the exact moment the bubble forms a perfect hemisphere. Pop! The bubble bursts immediately after. By tracking that characteristic spike in pressure, scientists can easily calculate the surface tension.
And finally, Part 5. Comparing liquid surface tensions.
So we've got mechanical, rotational, and pressure-based tools, but what does the data actually tell us? This table from the lab lays out the thermophysical properties, density, viscosity, and equilibrium surface tension for a few sample liquids at a rock-solid room temperature of 20 degrees Celsius. We've got water, reference liquids like D10 and N35, plus silicone and paraffin oils. The researchers found these tensions were wildly consistent across different batches, proving the tools actually work, but scanning these numbers, one liquid clearly stands out.
I mean, look at this massive difference. Water's surface tension is up at 71.8 millinewtons per meter. Compare that to paraffin oil at just 26, or silicone oil way down at 20. Water's surface tension is more than double that of those oils. This data perfectly proves just how incredibly strong water's cohesive intermolecular bonds really are. Those unbalanced forces at the surface of the water are gripping each other with tremendous strength to weave that tight, elastic sheet.
But hold on, all of those precise measurements were taken at a strictly controlled 20 degrees Celsius, which naturally begs the question, what happens to that tightly woven microscopic sheet when we turn up the heat?
The short answer? The barrier breaks down. As a liquid heats up, its kinetic energy spikes. The molecules start moving frantically, vibrating and bouncing all over the place. That chaotic movement physically disrupts those imbalanced cohesive forces on the surface. It literally tears apart that tightly bound barrier, which means as temperature goes up, surface tension drops right down.
So, to wrap up this explainer, what are our key takeaways? We've seen that surface tension isn't magic. It's an elastic sheet born completely out of unbalanced cohesive forces at a liquid's interface. We've explored how scientists tackle the invisible using some seriously ingenious mechanical, rotational, and pressure-based tools. We've got hard data showing water's uniquely strong surface tension compared to common oils, and finally we saw how temperature acts as a master switch, fundamentally altering those microscopic bonds.
It really changes how you look at a simple glass of water, doesn't it? If a slight bump in ambient temperature can so easily disrupt these tiny, invisible intermolecular bonds, it makes you wonder, how might these delicate microforces be silently shaping the massive, extreme, and ever-changing environments on our planet? I'll leave you with that thought. Thanks for hanging out for this explainer, and keep questioning the invisible forces all around you.